Okay, good morning or good evening. So let's continue speaking about the turbofans, what we call also the double flow engine, where we have two flows, the secondary flow and the primary flow. So this is an engine that is optimized, that is focused on decreasing the TSFC, decreasing the fuel burn. So cost economy from a point of view of the fuel, let's say. We have also said at the end of the last lesson that it was certainly not oriented towards optimization of the compactness. So the specific thrust, F divided by m dot, is not good, is low, so, and it should be high. So, and it's quite normal somewhere, because these two parameters from the beginning, we have tried to optimize them, and we have seen that we cannot optimize them both together. So we have seen that with the efficiency from the beginning, the efficiency is optimized, then the compactness is not optimized. And by decreasing and decreasing the TSFC, we have increased the efficiency. So this is clear that we are going further and further away from F divided by m dot, the compactness that is high, or the compactness, yes, that is high. So that is quite normal, and we have seen that with the turbofan. So we are going more and more and more towards TSFC reduction, so we are going into the opposite direction for the F over m dot. The F over m dot is worse and worse and worse. So this is quite normal. And that's why today we will also study a second cycle. It will be, in fact, our fifth cycle. That will be a cycle with what we call post-combustion or after burning. That will be there not anymore to fight against fuel burn, to reduce the fuel burn, but to go once again to the other parameter, increasing the compactness, increasing F over m dot. So let's say the opposite somewhere of the double flow engine. That will be the afterburning turbofan or turbojet, also an engine, let's say a cycle with post-combustion or afterburning. This is what will be the program of today. But let's continue first on the turbofan. The turbofan, so this is an engine, if we want to summarize that, this turbofan, this is also called double flow engine or double flow gas turbine engine. So where we have two flows, the primary flow, which is the central part, so that will be moving inside the core, as we have called that, of the engine, and we have said that we need to have a very high global pressure ratio. This is the high pressure compressor, where you have the m dot p, and this is the m dot secondary with the low pressure compressor that we have also called a fan, because there is only one stage. Behind that, you have the fuel flow, so you inject a certain amount of fuel. Behind that, you have a turbine that is driving the high pressure compressor, and you have a second turbine that is huge, most probably, we have explained that last week, that is driving the low pressure compressor. Of course, we have two exhausts, one for the primary flow that will create a V-jet primary, and we have one here for the secondary flow that will create V-jet secondary. Of course, you have one intake that is here in front. So you have one intake that is here in front, and here in the intake, of course, you have the m dot total. And in front, you have in cruise a fictive divergent like this, and you are absorbing the air through the section AA here. And we have also said at the end of the last lesson that there are now two A5, a A5 primary and an A5 secondary. Okay? And of course, we have introduced new sections if we want to give a complete drawing. So it's still the section 3, where we have the TT3 that is equal to the TIT. We still have the section 4 here. If you want, you can introduce a section 3.5 here. This is still the section 2. This is still the section 1. And this section is the section 1.5. Okay? And you have also, I indicated that last week, two nozzle pressure ratio. A nozzle pressure ratio secondary, which is equal to PT 1.5 divided by PA. And here you have a nozzle pressure ratio primary, which is equal to PT4 divided by the same PA. This is the engine that we have created. And what is the result of this engine? The objective is to reduce the TSFC. This is the objective we have. Of course, the thrust divided by m dot, as I indicated, is not good. This is low value. It's not a good point. It's not good as an objective. But we have a huge thrust. This is a kind of summary. How much is the TSFC? I indicated you in sea level static ESA conditions for the turbojet, it was about 1.0 kilo per decanewton hour. Here, for a turbofan with a bypass ratio that we want to be high, let's say around 10, you will be at only 0.30. So you have reduced the thrust, the TSFC by a factor 3 at least. Okay? And for that, we have indicated, this is, let's say, the second way to summarize the situation, that we have introduced, in fact, more complexity in this engine. Because compared to before, where we had two design parameters, it's TIT, in fact this is TIT divided by TT1 that we should write, and the pressure ratio, we have introduced two new parameters in the design ones. One is the bypass ratio, that is equal to m dot secondary divided by m dot primary. And also we have introduced PF, or PLPC, which is the pressure ratio of the low pressure compressor, that is equal to PT 1.5 divided by PT1. Okay? And we have also called the pressure ratio P global, which is equal to PT2 divided by PT1, which is equal to the pressure ratio of the low pressure compressor or fan multiplied by the pressure ratio of the high pressure compressor. And the thrust divided by m dot, and the TSFC, these are different functions of these four design parameters. So this is thanks to the higher complexity of the engine that we are able, of course, to reach this lower TSFC. And for that, we have explained last week, what are we doing? We are selecting the bypass ratio. We are selecting the bypass ratio as high as we can. I'm coming back on that in a minute. Let's say 10 or even more. we are selecting the TIT, as always, extremely high. We are taking the P global also extremely high. Maybe in modern engine this is 50 or more. Can you imagine? So in the combustion chamber, so you take a combustion chamber like this one, you take a combustion chamber like this one, and here inside the combustion chamber you have a pressure of 50 bar at takeoff. So you see the thin plate that we have here, and here we have 50 bar. 50 bar at takeoff. So huge pressure inside the system, and we have also the PF, that we have selected as small as possible. So the PLPC is as small as possible, so one stage, this is a fan, maybe only today in modern engines only 1.4. And the very high BPR means that m dot secondary has increased enormously. Because, put that in your mind, what we are doing is that we are comparing the turbofan to the turbojet that has the same core. The same core. So what are we doing? We say for the turbojet and we say for the turbofan that we have the m dot primary is the m dot, the m dot primary is the m dot of the turbojet. The pressure ratio of the turbojet is now the same as the global pressure ratio. So that means, for example, you have the same TT2. The TT2 is the same in both cases. We fix also the same TIT. So that means that the fuel flow is also the same in both cases. In the comparison, we have the same core. That means, let's say, the same combustion chamber. Same combustion chamber. So same mass flow rate at the entrance, same pressure, same temperature at the exit, same fuel flow that is injected. That's why we are comparing apples and apples. So we are comparing two engines at their point of view of same fuel flow, but with a much, much, much higher thrust when you increase and increase the bypass ratio. So this is the point of comparison we have. And of course, this is delivering, let's say, problems. What are the problems you will have? You see, I have already indicated this is the low pressure turbine and this is the high pressure turbine. The low pressure turbine is a very difficult task because the low pressure turbine must drive the low pressure compressor with a very low mass flow rate. You need to drive a very large mass flow rate. In order to give order of magnitudes, here you have 100 kilo per second, and here you have 1000 kilo per second.